Hi, we're part of the team of the Expressive Computation Lab at UC Santa Barbara. Our team members are Ashley del Valle, Mert Toka, Alejandro Aponte, and Jennifer Jacobs. We will present our work titled PunchPrint, creating a composite fiber-filament craft artifacts by integrating punch needle embroidery and 3D printing. Through manual textile production, craft people can create intricate, colorful textiles in a wide variety of patterns and textures through techniques like weaving, knitting, and crocheting. Digital fabrication offers a unique opportunity to extend textile craft practices through 3D printed textiles. Researchers have explored a range of additive fabrication methods to produce flexible materials with similar properties to fiber-based textiles. Designers can control the functional and aesthetic properties of 3D printed textiles by specifying the material and digital fabrication behavior. Nonetheless, 3D printed textiles are limited compared to traditional textiles. 3D printed textiles are entirely fabricated of extruded thermoplastic filaments. These materials have a different visual and physical properties compared to fiber-based textiles. So far, 3D printed textiles still lack the look and feel of traditional fabrics. We seek to develop methods to combine established forms of manual textile craft with domain-specific methods for additive fabrication to support new forms of personal textile production. In doing so, we see opportunities to enrich both 3D printing and manual craft. We present PunchPrint, a technique for integrating filament and fiber-based textiles by combining the 3D printing of a parametric fabric substrate with punch needle embroidery. Punch needle is a form of manual embroidery. Craftspeople commonly use punch needle textile to produce craft artifacts, ranging from decorative pieces and accessories to garments. To make punch needle embroidery, the craft person uses a long needle to push a continuous strand of yarn into a foundation fabric, creating loops along the back and flat stitches on the top of the fabric. Unlike regular embroidery stitches, which interweave yarn back and forth between the fibers of the foundation fabric, punch needle structures rely on the fabric tension to hold stitches in place. Punch needle is a versatile craft, yet craft people are limited to using specific foundation textiles. Thin, lightweight fabrics can easily and irreversibly break, fail to adequately tension the loops, and create loops with inconsistent height. Foundation textiles are usually thick and stiff to maintain adequate yarn tension and withstand the punching process. Additionally, they fray easily if unsecure, which can lead to a laborious post-processing to secure the fabric edges.
We analyze the workflow and constraints of traditional punch needle practice to identify the following design goals. First, we seek to develop a 3D printed textile that can vary in flexibility, thickness, and density while maintaining a structure that is robust enough to support manual punch needle stitches. We also aim to extend the design space of punch needle embroidery by incorporating affordances of filament-based textiles while also broadening the aesthetic and textural qualities of 3D printed materials. Lastly, we strive to support new workflows in punch needle craft assembly. We seek to integrate construction methods from both 3D printing and traditional textile craft to create new opportunities for punch needle craft. The initial component of our technique is a 3D printed foundation fabric. We mimic the woven structure of fiber-based foundation fabric by 3D printing a TPU-based grid structure that reproduces the behavior of textile fibers while providing visible holes for needle insertion. The second component of PunchPrint is a parametric design tool. We integrated our fabric toolpath process into a parametric design tool for craft people to control fabric properties and integrate other design elements into the print. First, we'll describe the foundation fabric development process before describing our design tool.
Traditional punch needle foundation fabrics are comprised of vertical warp and horizontal web fibers woven tightly together. When the punch needle goes through, its fibers move outwards, and when the needle is retracted, neighboring fibers contract and force the yarn to stay in place. We designed PunchPrint fabric to resemble this construction using intersecting filaments. We print horizontal and vertical filaments in two fused layers, creating two-dimensional grid structure. In the PunchPrint fabric, the filaments stretch outwards as the needle goes through and compresses as the needle is withdrawn, keeping the yarn in place. Commercial slicers like Ultimaker Cura support grid and line infill methods that can produce a visually similar grid structure to PunchPrint fabric. These methods create robust structures for rigid volumetric prints, but introduces weak points for flexible sheets with a small number of vertical layers. These weak points increase the likelihood of fabric breakage when the punch needle pierces through. Due to the limitations of existing 3D printed methods, we sought to develop a new tool pathing technique that produces a fabric capable of withstanding the punch needle process. Our fabrication method is a hybrid between the grid and line 3D printing infill methods. We substantially reduce material weak points and defects created by individual infills, while optimizing the thickness and flexibility of the resulting 3D printed fabric. We extrude fresh material at 175% of the layer height with a 20% flow rate increase, resulting in continuous material flow and strong layer adhesion at the intersection points. We integrated our fabric toolpath process into a parametric design tool for craftspeople to control fabric properties and integrate other design elements into the print. We implemented a grasshopper component with 3 parameters for controlling fabric structure. Outline accepts any closed planar curve as input. EPI controls the fabric density, and the stiffness is the number of vertical layers of the fabric. By adjusting sliders for the API and stiffness and altering the input curve, the craftspeople can produce a range of fabric geometries with different structural properties. In addition, we developed a workflow that allows pre-sliced 3D geometry to be incorporated into our fabric to leverage the highly optimized toolpaths of commercially available slicers. PunchPrint fabric can be worked in almost exactly the same way as traditional punch needle fabric, with the important exception that the fabric structures don't need to be held in a frame or a hoop. This is due to the fact that PunchPrint cloth can be pierced with less force than fiber-based fabric. Nonetheless, it is also possible to use our fabric in an embroidery hoop.
By integrating punch needle methods with 3D printed textiles, we can expand the applications of both domains. Here we demonstrate the expressive potential of PunchPrint to fabricate composite garments with 3D printed and fiber-based textile structures. We use PunchPrint to fabricate a reversible wearable bucket head. This example shows how PunchPrint supports the construction of punch needle garments that can be shaped or bent to fit the body comfortably. This piece exemplifies how PunchPrint enables the creation of highly bendable 3D printed textiles by augmenting the method of textile garment sewing to create a reversible garment. Crafting small-scale punch needle pieces like jewelry can be challenging since they require a high degree of manual skill to produce small, consistent stitches, and the post-processing of small-scale items is difficult. We developed 2 monarch butterfly-themed earrings to demonstrate how PunchPrint facilitates small-scale punch needle embroidery artifacts. We showcase how we can build on common assembly methods in 3D printing to fabricate 3D punch needle structures, and re-envision common hobbyist 3D printing projects in punch needle form. Inspired by the common desktop 3D printing chess set project, we created a press-fit knife piece.
We explored the long-term use of PunchPrint artifacts. As a starting point, I performed a durability test by fabricating a PunchPrint iPhone case and using it for 55 days. These initial results are encouraging. Aside from minor fiber compression and visible wear on lighting yarns, the case has held up and all yarns remain in place. These opportunities come with a trade-off. Unlike the largely automated fabrication of thermoplastic textiles, PunchPrint textiles require manual fabrication. PunchPrint, like other forms of 3D printed fabric, relies on the fabrication of non-biodegradable plastic. In an effort to reduce the waste created by 3D printed textiles, we are exploring how our method can be used to produce attractive, durable, and repairable artifacts. So far, the results are encouraging. Here we show the process of repairing PunchPrint fabric with a 3D pen. We are excited about the potential of PunchPrint to broaden the expression space of both additive fabrication and manual textile crafting. In the future, we see opportunities to further explore the design space of 3D printing and punch needle by evaluating our method with fellow punch needle crafters. Thank you, everyone. We hope this presentation has been useful for your research and inspired new ideas for supporting the integration of craft and digital fabrication.